In order to understand or begin to understand what electrons do, we first have to take a quick trip into physics and look at electromagnetic radiation, light. The interaction of light with atoms is one of the things that really helped scientists to understand what's going on inside the atom. So we need to understand a little bit about light. It's a form of electromagnetic radiation. Light is a type of energy. It travels through space at the same speed. It's called the speed of light. 3 times 10 to the 8th meters per second, which you probably don't have a good grasp of how fast that is, 186,000 miles per second. Okay, that's fast, isn't it? I remember watching the cartoons, some of those really old cartoons, and you see this old geezer, and he blows out the candle, and then he goes and he jumps into bed before it gets dark. Is that possible? No, because light travels so quickly that you couldn't possibly do that. Light travels faster than sound. That's why we see the lightning, and later we hear the thunder. You can estimate how far away the storm is by counting the difference in time between when you see the flash and when you hear the sound. Light travels very, very fast. And light always travels at the same speed. Always the same speed. Light is interesting. It has properties of waves and of particles. If we think about waves, it's easier to think in terms of waves on water because we can see those. We can't see light waves, we just see the light. So if we think about a still surface of water and dropping some droplets of water into it, we get these ripples, right? And the ripples move out from the center, and they keep going, and then they gradually fade away. These are waves. The wave is carrying energy. This droplet of water comes in, and it has falling, it has kinetic energy, and that energy goes somewhere. Energy is transmitted through the waves. Have you guys been to the ocean? And you stand in the surf, and that wave comes. And if a big one comes, it might knock you over, right? Is there energy in that wave? Yeah, there's a lot of energy in that wave. So waves carry energy. So this is an illustration of a light wave. It's a sine wave, if that means anything to you. Up and down, up and down, up and down. And we have, we quantify this. There's a wavelength, and that's the distance from one peak to the next, or you can call that a crest, or you could measure the distance from one trough to the next, or this part where it crosses the middle is called a node. So from this point over to here, that's a wavelength. It's the length of one wave, right? And for visible light, the difference between red and blue and yellow is how long the wave is. It's all light, it's all traveling at the same speed. So the wave is always traveling at the same speed for light, but the wavelength is going to be different. White light has all the colors of light in it, and we can separate it using a prism. So here's a prism. It's a triangular piece of clear, it could be glass, it could be certain kinds of plastic as well. And the reason it separates these into, separates the light into different colors is that the light interacts with this material as it passes through. There's a surface here and a surface here, and it causes the light to bend, and the different wavelengths of light bend a different amount. And so we get the separation, and we see a rainbow. This also happens in little droplets of water. That's why we see a rainbow. It can also happen, it happens in my house at certain times of the year. There's a chandelier by the front door, and when the sun hits it, it sends little rainbows all over the house. You know, the kids are like, woo! How cool. The white light has all the colors, and when you separate it, you see this continuous spectrum. It's always in the same order: red, orange, yellow, green, blue, indigo, violet. because those are the different wavelengths of the light. When we see color, here the woman in this picture has a red shirt. The shirt appears red to us because the material in the shirt is reflecting the red light and absorbing the other colors of light. And so the red light comes to our eye, and our brain interprets that and tells us, oh, that's red. And, yeah. So I think we all understand, having grown up in the valley where the sun is really intense in the summer, right? Which is going to cause you to be hotter practicing baseball, wearing a black shirt or a white shirt?
Black shirt.
Black shirt. You're just going to die, right? And if you have a black car, you know that car gets really hot in the parking lot. Because anything that appears black because it's absorbing almost all of the light. That's why it's very difficult to get a good photograph of a black animal, like a black lab or, some other sort of, black cat. You take a picture of them, they just look like this dark area. It's hard to get any good pictures of them because they really don't reflect much light at all. A white shirt or a white car reflects most of the light. And there's energy in light. That sunlight makes things warm when things absorb the energy. And that's why the asphalt gets so stinking hot. It's absorbing the energy of the light. Another parameter of the wave nature of light is called the frequency. The frequency has the symbol nu, which is a V with a curvy side. Thankfully, we don't end up using this a lot in this class. So this is nu, this is V. They look pretty similar, don't they? So that's V, that would be velocity. This is nu, which is frequency. The frequency is the number of waves that pass a given point in a certain amount of time. The number of cycles or crests that pass through a stationary point in 1 second. And so the unit here can be per second, which is the same as hertz. And hertz may be maybe a unit that you've heard of. It's cycles per second. So, a 60 kilohertz something is going to have 60,000 cycles in 1 second. The wavelength and frequency are inversely related. The shorter the wavelength, the higher the frequency. I can't remember if I have a picture on the next page or not. Nope, I don't. So I'll draw you a picture here. My pictures are kind of sad. So I can't talk when I do that. Well, I can, but then it gets really ugly. Okay, so there's two really crummy looking waves. Here's the wavelength of that one. That has the symbol lambda, which looks like an upside down Y. And then here's the wavelength of this one. Both these waves are traveling in that direction just because I say they are. How fast are those waves going? I don't need the number. The speed of light, right? They're both traveling at the same speed. So imagine that someone is standing here counting the waves, the crests of these waves as they go by. They're both moving at the same speed. Is he going to have to count faster for the top one or the bottom one? The bottom one. In the same amount of time, this bottom one is going to have a lot more crests pass through. That's the frequency. The frequency is high. 1, 2, 3, 4, 5, 6, 7, right? And the top you're going 1, 2, 3. So this one is low frequency, and this one is high frequency. Which one has the shorter wavelength? The bottom. So this is low wavelength equals high frequency. Low frequency equals high wavelength. So if one's big, the other is small because they're traveling at the same speed. So light is a wave. Light can also be viewed as a stream of particles. You ever heard of a piece of light? I'll take 3 pieces of light, please. No, you've got light or you've got no light, right? But light actually acts like a stream of particles sometimes. And a photon, which I'm sure you've heard of, a photon is actually a particle of light. Well, they always say in Star Trek, fire the photon torpedoes, right? How could you have a torpedo made out of light? Light has a lot of energy in it. I don't think we've figured out how to make a photon torpedo yet, but it could be possible. So a photon is a particle of light, a single packet of light energy. Light is energy, and this is a small piece of energy. So, you put a whole bunch of those together. Could it be destructive? Yeah, probably could. The amount of energy that's carried in that little packet depends on the wavelength of the light. A shorter wavelength will have greater energy. The light waves carry more energy if their crests are closer together. So high frequency, short wavelength, greater energy. So that can be a little difficult to remember. I'm going to draw 2 waves again. Oh, that one's really bad. Now this isn't very scientific, but which one of those looks more energetic? The top one, right? You think of jumping up and down, a lot of activity. This looks more energetic. That does have more energy. This one looks slow and lethargic. They're traveling at the same speed, but this one, you're going to have a lot fewer crests, right? Think about standing in the ocean, close to the shore, right? And waves are coming in. If they're just slow waves, okay, fine. But what if they tripled in speed? Would you notice that? Yeah, it's like I'm getting pummeled by these waves. I'm getting out of here. I can't take this anymore. So when they're coming closer together, that's higher energy. I personally have, I have to think it through to remember the relationship between wavelength, frequency, and energy. It's not something that I just have crystal clear in my mind. I actually think of something like this in my brain and figure it out every single time. Because I don't do calculations with this stuff all the time. And you won't either. So, any questions?